In this lecture, we will be discussing about one very popular machine learning model, what we call support vector machines. Let's start with an example. So here we are given two sets of points. So some are blue dots and some are represented through green dots. If you want to learn a linear classifier, for example, a logistic regressor, here we have a purple model, and you can see that the model was able to correctly classify all the data points. And here you have another model, a red model, I will call it. It also was able to classify the data points accurately, okay? So now we have two models. One is the pink model and the other one is the red model. Which one would you prefer, okay? So let's look a little bit thoroughly about the pink model. The general idea is that we will move the pink model vertically in each direction, okay? So if you do that, then what will happen, then we will stop at when the model actually start touching the data points, okay? So here we have the first blue data points touched by the pink line if we move to the left, and here the same model or line will move to the green data point, okay? So think about this, that the pink model, you are actually moving towards the data points direction vertically, and when you touch at least one of the data points, you stop, okay? So that will give you a kind of rectangular region or a tube, whatever you call that, we represented through this rectangle. Let's do the same for the red model, and it will give us a tube like this, right? If you follow the same analogy, okay? Now, if we put those two models side by side, you will learn that the red model is actually a better model in terms of the width of the tube, right? And if you look at the data pattern, you will see that for the blue model, because we see a kind of Gaussian-like pattern here. So if you have a data point blue here, then the model won't be able to catch it, okay? Likewise, if you have a green data point here, the model won't be able to catch it, okay? But I think the red model has a much wider breadth in terms of more learning the distribution of the data points. But anyway, the whole idea of this support vector machine is actually learning this tube, and that's why it also known as maximum margin classifier, okay? It's learning the margin that a linear model can give to explain the data point, okay? So in terms of optimization, what happens that we are talking about a linear SVM. So this would be the final solution, right? The red model, okay? But how do we actually get to this point, okay? So in terms of optimization, this is what we have to maximize. So B being the intercept and W being your parameter vector, and this red linear model, or this red line being a linear model, the optimization function is actually your intercept divided by the norm of W. So that's the maximization function for linear SVM. So that's the general idea. I'm not going to the full depth of the mathematical formulation. Another thing we need to learn that even SVMs are linear models, but they can do pretty good job classifying or modeling non-linearity, okay? So for example here, but we need to learn that is done through some kind of transformation of the features using some function, what we call kernel functions. So here your parameter is actually linear, but your data points, even it is linear, we can transform it to some non-linear space, okay? But keep it in mind that the model is still a linear model, okay? And there are a lot of different kernel functions you will be learning: polynomial kernel, Gaussian kernel, or sigmoid kernel. But you need to keep in mind that the model is linear, but those kernels actually transform the data points in non-linear space, where the data points actually are classified in a non-linear way. Okay, but the model is still linear. Okay. Hope this helps. If you have any question, feel free to ask me. Thank you.